I'm so excited. Man, I forget that one television. I forget that one movie where it was that one TV show where this kid was like, oh, it was Boy Meets World. You have not seen Boy Meets World? Bunch of sinners. Well, there was this kid named Mr. Meekus who was like, who knew everything. And he was like the class, he was the teacher's pet.
Apologies to the online people who are waiting for me to get this thing going. Just takes a while. Are we up there yet?
You know the guy that played Mr. Feeney, he's 91 years old. He was in the news that he stopped a burglar in his house. He's 91 and a burglar tried to enter his house and he stopped a burglar from entering his house. And I'm like,
there we go.
Don't mess with Mr. Feeney.
All right. Looks like we're there. 5.1, page 239. Exercise 1 through 5. Identify the underlined item as a cardinal number, an ordinal number, or a nominal number. Now, nominal is the fancy name for it. The textbook calls it identification, but sometimes you'll see that word nominal used out there. So, do you know the difference between cardinal, ordinal, and nominal? Now, think a minute. Ordinal would sound like what? The order it's in. Cardinal sounds like a bird. So I don't know what to do with that one. Nominal sounds like a name. You follow me? Or in the textbook, since they use the word identification, identification would be your name, identifying who you are. So what does that make cardinal mean? It's not a bird, it's how many. Cardinal means how many. You go, why? It ought to be a bird. Well, think of how many birds are there. Somehow figure out a way to make those words connect in your mind mathematically, or just write yourself down some notes. I'm amazed that more of you don't bring notes to your exam. What, is that embarrassing or something to have notes? You're not supposed to have all this stuff in your head. Just put it on paper and bring it with you. You say, well, I don't know exactly what to bring. Then bring everything. Never hurts to have too much information. But problem number 2, this is the second problem in this exercise. Is that cardinal, ordinal, or identification? Are we saying how many exercises there are? Or are we saying what's the order of the exercises? Or is that the name for that exercise? Anybody want to guess? You don't. It's ordinal. The second, whenever you see first, second, third, fourth, fifth, that's not how many, that's not name. First, second, third, fourth, fifth, that's ordinal. That's the order in which the numbers occur. Well, I can see already this is not going to be an easy exercise, is it? I'm going to give some of you a headache today, it looks like. So write down some notes. Problem number 4. 1, 2, 3, go. What?
Cardinal.
Are we counting how many people in the race? Or are we saying, watch what we're saying. On your mark, get set, go. What would that be? Ordinal. Ordinal. You're not going to like this, are you? Number 6. 3 numbers on this check here. 3 numbers. 14, 5696, and 0166. Which number is cardinal? Which number is ordinal? Which number is identification? Which one identifies which check this is?
0160.
Which one? Okay, now where's 14? Up in the right-hand corner? So what check did they write before they wrote this one? And which one will they write next? 15. So what would that make 14? Ordinal. Good. And then 5696, what is that?
The amount.
That's the amount of money. If the amount would be how much, what would that be? What did I just tell you cardinal stands for? How much or how many. So what does that make 5696?
Cardinal.
That makes it cardinal. So what's left for 0166?
Is that nominal?
We've used ordinal, cardinal, so what does that have to be? Nominal, or by the textbook's terminology, identification. You go, what is that? Okay, have you ever looked at a check that you've written? You say, I don't write checks anymore. Okay, if you looked at a check, that's your account number. What's that all about? That's your account number. So that identifies who the money's coming from. That identifies the account that they're going to get the $5,696 from. You got it? If you don't, just practice it 3 or 4 times till it starts to stick in your head. Write yourself some good notes that make sense to you. In other words, just writing down what I say isn't going to necessarily make sense to you, but give yourself some good notes that make sense to you, and then you'll be able to remember it down the road. Problem number 8 through 10. What did I do with 7? Oh, that's yours. Oh, number 7 says, continue the sieve of Eratosthenes in figure 5.1 on page 231. Well, I just thought rather than you have to do that, I just went to the internet and found prime number chart and calculator and printed it off and gave you a copy of it. So you have all the prime numbers on this little piece of paper up through, what, 100?
1,000.
1,000. So you've gone way beyond what problem 7 told you to do. So problems 8 through 11, use figure 5.1 or use the chart that I just gave you to find how many prime numbers there are between 1 and 25. Pick up your chart. Do you see 1 on it? No, because 1 is what?
Not prime.
It's not a prime number. Do you see 25 on here? No, because 25 is not a prime number. So what prime numbers are between 1 and 25? 2, 3, 5, 7, 11, 13, 17, 19, and 23. You got it? You see how to use the chart? There you go. Number 10. How many prime numbers between 50 and 75? Get your chart again. Where's 50? It's between 47 and 53. Where's 75? It's between 73 and 79. It's not listed because this is a prime number chart. So how many prime numbers between 50 and 75? 53, 59, 61, 67, 71, and 73. You follow the process? Everybody see where I'm getting my numbers off this chart? Good for you. Number 12. Refer to figure 5.1, that's your chart again, and find the smallest prime. What's the smallest prime? 2. Find an even prime.
Also 2.
That's also 2. Everybody got that? Good. Number 14. Primes that differ by 2 are called twin primes. The smallest twin primes are 3 and 5. Because between 3 and 5, there are two numbers. No. Oh, from 3 to 5 is 2. Subtract 3 from 5, you get 2. So you subtract 5 from 7, do you get 2? Yeah. So subtract 7 from 11, do you get 2? No. 11 from 13? So you see what happens? Twin primes. Find two other pairs of twin primes. There's a whole bunch of them. You could pick any two of them. Number 15. That's your problem. Skip it. We got enough to do without messing with that today. That means we move to number 16. In problems 16 through 21, find all the factors. What do they mean by factors? The divisors. All the numbers that will divide into number 16 to 28. How many numbers will divide into 28? 1, 2, 4, 7, 14, and 28. You follow that? How did I find those? Anybody want to guess?
1 times 28 is...
I just said, can I divide 28 by 1? Yes. Can I divide 28 by 2? Yes. Can I divide 28 by 3? Evenly? No. Can I divide it by 4? Yes. Can I divide by 5? By 6? No. By 7? Yes. By 8? No. By 9? No. By 10? No. You follow me? I just keep working my way up, and I write down the numbers that will divide evenly into 28. And that'll get you there. And I just did what they said to do. I found all the factors of 28. Just remember, some people will put down 2, 4, 7, and 14, and they'll forget about 1 and 28. But 1 and 28 are also factors of 28. Okay? So don't overlook those two. Number 119. Where does 119 come from? Oh, that's number 18. It's not 16. It's 18. Well, you made a mistake, Tom. So, what can I divide into 119? I know I can use 1, and I know I can use 119. Now, what else?
Can you use 2?
2 into 119 would be, 2 will go into 120,
Oh, that's right.
but not into 119 evenly. Can I use 3? Can I use 4? Can I use 5? And you know, you say, isn't there an easier way to do this? Yeah, I'll get a calculator and just punch in 119 and go divide by and see till you find the ones that work out even. Okay? Well, that's enough of that. That'll keep you busy for a while, won't it? Problem 22 through 27, find the prime factorization. Oh, that ought to be in the Nelson Atkins Museum of Art. Doesn't that look pretty? That's called a factor tree. It does kind of look like a, I mean, I could have spread it out more to look like a Christmas tree. I just look at these and it just warms my heart. You look at it and it gives you a headache. I'm sorry. But you see what I did here? It's like find the prime factorization. So that means, prime means I want all these numbers to be prime numbers. And factorization means I want factors of 24. What are factors of 24? Well, 4 times 6 is 24. You follow me? And what are factors for 4? 2 and 2. And what are factors for 6? 2 and 3. So now I have the prime factorization for 24. In other words, 24 is the same as 2 times 2 times 2 times 3. You got that? Now you say, I did it again a different way, because I want you to know there's more than one way to get there. 24 is the same as 2 times 12, right? And 2 is already prime, so I just keep 2, and 12 is 3 times 4. Everybody follow me? And then 2 and 3 stay the same, but 4 becomes 2 times 2. So I still have the same prime factorization. 2 times 2 times 2 times 3. You follow me? The order doesn't matter. Let's try it one more way. 3 times 8. Well, I keep 3, but 8 becomes 2 times 4. And then keep the 3 and keep the 2, and 4 becomes 2 times 2. So I still have 3 times 2 times 2. You follow? It doesn't matter which way you start factoring, you're going to eventually end up at the same place with the same prime factorization for 24. And someone's probably thinking, why are we doing this? And it's because it's so much fun. Okay, we'll use it later on to simplify fractions. Were some of you taught to do this, to simplify fractions earlier in life? Ah, and it helps, doesn't it, to simplify fractions. So that's the reason for learning it. That's the real reason for learning it. The other reason is it's just fun. Let's do 24. Problem 24. 82. Now, I say, okay, I just pick a number and I say 2 because I know it'll go into 82, and that leaves me with 41. What do I do with 41? You go, I don't know. Pick up your prime number chart. And what do you see when you get to the prime number chart? 41's on there. So what does that mean? 41 is a prime number, so I've already put it in primes. See why that chart helps you? When you're looking at it saying, maybe that's a prime number. And if 41 wasn't prime, then I have to figure out what to do with it. See, like number 26, 191? Check the chart. Is it on there? So, what's the prime factorization? 1 and 191. You follow me? It's already prime. All right. That's enough of that. Let's go to 28 to 31. What's 28 to 31 say? Find the natural number whose prime factorization is given. So here they said 2 and 3 squared and 5 squared. So what that would really be is that would be 2 times 3 times 3 times 5 times 5. Everybody see where I get that from 2 times 3 squared times 5 squared? And this is 2. 3 squared is 9. 5 squared is 25. What's 2 times 9 times 25? Well, that's the same as 9 times 50. And what would that be? 450. So, 2 times 3 times 3 times 5 times 5 equals 450. Do you like that? Does that look right to you? Or do in your heart of hearts you feel like something's wrong and you should change it to make it look right? Now do you see how the guy on the test is going to mess with your head? He's going to put a number down that looks better, and some of you will be inclined to pick the one that looks better, because 2 times 3 times 3 times 5 times 5 is 450. If you don't believe me, get your calculator out and punch 2 times 3 times 3 times 5 times 5 and tell me what you get. Do you get 450? Yes. And you don't like it because it doesn't fit your little frame of reference. Well, you need to adjust your frame of reference. Number 30. I'll leave that one now and you can look at it a little bit because it takes a while to fix it in your mind. Number 30. 2 times 3 times 5 times 11. I just did 2 times 5 and got 10, and 3 times 11 and got 33, and that comes out to be 330. And does that look like 2 times 3 times 5 times 11 is 330? I mean, doesn't the answer just automatically, when you glance at it, look too big? So get used to realizing that your heart is going to tell you that answer's too big. So then do the math again and say, no, the answer's right. I just have to, my heart is deceitful. And I have to recognize that. Is this number divisible by 2, by 3, and by 5? And the first one is 468. Is 468 divisible by 2? Yes. How do you know that? What's the rule for divisibility by 2?
Even number.
It's an even number. Is it divisible by 3? Yes. How do you know that? What's the rule for divisibility by 3? Who was taught that? See, you were taught divisibility by 2, right?
Yes.
How many were taught divisibility by 2? Apparently they thought if you know how to do divisibility by 2, they don't have to teach you by 3. This guy wants you to know by 3. Does anyone know the rule for divisibility by 3? Yes.
I do.
What is it?
It's anything that can go into 3 how many times?
Okay, but now how do I know this number is divisible by 3?
Because it's an odd number. Well,
No, it ends in an 8.
no, that is correct.
Do you have it? Do you know the rule? What
Yeah.
is it?
You add all those numbers together, and if that number is divisible by 3,
You add 4 plus 6 plus 8. That is so dumb. And you get what? 18? And if 18 is divisible by 3, then this number is divisible by 3. That is so dumb. Who cares? It works, doesn't it? Write that rule down. For divisibility by 3, you add the digits, and if the sum of the digits is divisible by 3, the number is divisible by 3. Now, you probably know the rule for 5, don't you? What's the rule for divisibility by 5?
Ends in a 0 or a 5.
Ends in a 0 or a 5. So we say, nope, it's not divisible by 5. You follow what's going on? If you don't have those 3 rules in your head, you put them on a piece of paper next to you. In fact, write them on the back of your little chart. That's what I did here. I just wrote them on the back of my chart in case I forgot them. When you get old, have you heard of a senior moment? When old people forget things? So I write this stuff down just in case I forget it. All right, let's do 580. Is it divisible by 2?
Yes.
Is it an even number? Yes. Is it divisible by 3? What's 5 plus 8 plus 0? 13. Is that divisible by 3? No. Not evenly. Is it divisible by 5? Ends in a 0? Yes. 795. Is it divisible by 2? Doesn't end with an even number, so no. Is it divisible by 3? I don't know. 7 and 9 and 5 add up to what? 21? Yeah, that's divisible by 3. Yes. Is it divisible by 5? Ends in a 5, so yes. 3942. 3,942. Divisible by 2?
Yes.
Yes. Divisible by 3? Let's see. 9, 10, 11, 12, 16, 18. Yes. 18 is divisible by 3, so yes. Divisible by 5? No. There you go. It's easy if you have the rules handy, isn't it? So keep those rules handy. Number 34. Find the smallest whole number, multiple of 4, that leaves a remainder of 1 when divided by either 5 or 7. the smallest multiple of 4. So what are multiples of 4? 4, 8, 12, 16. You understand I'm just adding 4 each time? You can take your calculator and go 4 plus 4 equals, and you'll get 8. Then 8 plus 4 equals, you get 12. 12 plus 4 equals 16. And you just keep going. 24, 28. This is what, oh, I just quit there? Why did I quit there? I don't know. I thought I went further than that with it. Well, multiples of 4, that leaves a remainder of 1 when I divide by 5. So, 4 divided by 5 leaves a remainder of 4. 8 divided by 5 leaves a remainder of 3. 12 divided by 5 leaves a remainder of 2. 16 divided by 5 leaves a remainder of 1. There it is, right there. You follow that? 16. Or 7. 4 divided by 7, remainder of 4. 8 divided by 7, remainder of 1. So what would that be? Oh. Yeah, but that's not the same number. Those are two different numbers. I want to keep going till I find one. I should have gone farther because that one's 8. Where do I find the one that both of them will divide by? Oh, let's see. If it has to divide by 7 and it has to divide by 5, I want something divided by 7 and 5. I want to divide by 35. And I want this divided into here to give me a remainder of 1. Well, let's see, 36 would work. 28, what's next? 32, then what's next? 36. There it is. There's the one that works for both of them, doesn't it? 5 times 7 is 35, remainder 1. 4 times 9. Oh, 3 or 5. I should have said 4. 5 or 7. 5 times 7 is 35, remainder 1. 7 times 5 is 35, remainder 1. So there's the magic number. Well, that was fun, wasn't it? 36 to 45. In problems 36 to 45, find the GCF. Does anyone know what GCF stands for? The greatest common factor. Okay, what are factors of 14? 2 and 7. You with me? What are factors of 210? Primes? 7, 2, 3, and 5. Now, what's common? What's in both of those? A 2 is in both. And what else? A 7 is in both. So the greatest, what did they want to know for 36? The greatest common factor of these two numbers, what's 2 times 7? Is 14. You see how you can use that prime factorization stuff to figure this out? You draw your factor tree down to where you have prime numbers, then you look to see what's common. Now I'm going to do something else here that I hope doesn't confuse you, but my past experience has been that people seem to get a handle on the greatest common factor And then when we study the least common multiple, they get confused. So I'm thinking I'm going to try something today that teaches both at the same time with the same numbers. Least common multiple. Okay, what are multiples of 14? 14, 28, and then 28 plus 14 is what? 42, and 42 plus 14 is 56, and 56 plus 14 is 70. You see what I'm doing? I'm just multiples. Multiples of a number just mean you keep adding a number, and this would be 1 times 14, 2 times 14, 3 times 14, 4 times 14, 5 times 14, 6 times 14, 7 times 14. You follow what's going on? And I just keep writing them out here because it's so much fun. And then my other number was 210. So the first one is 210, the second one is 420, the third one is 630. But now because I made this chart out here, see what happened? I got out here to 210, and 210 is one of these. So I found the least common multiple. So the least common multiple is 210. But watch this. I mean, you can do it that way and find it every time, but watch this. If this least common multiple, a big old box, is going to have 14 in it, it has to have a 2 and a 7. Everybody follow that? And if it's going to have 210 in it, it has to have, along with the 2 and the 7, a 3 and a 5. So I've built a box that has both numbers in it. And when I take 2 times 3, 6 times 5, 30 times 7, I get 210. You see how you can use prime factorizations to find least common multiples as well as greatest common factors? And your job is to keep those two separate in your minds as to when they want you to find the greatest common factor, when they want you to find a factor, and when they want you to find a multiple. A multiple and a factor. We'll come back to multiples later on, and if that messed you up, I'm sorry. I meant to be helpful. Let's do 38. GCF, greatest common factor for 315 and 350. I've already built a tree for 315 to expedite time. Let's do the one for 350. This is 5, and 70 is 7 times 10. Everybody follow that? So I have 5, 7, and 10 is 2 times 5. You follow that? So what's common? What's common to both of these? Is there a 3? No. Is there a 5? Yep, so I put a 5 in here. Is there another 3? No. Is there a 7? Yes, so I put a 7 in here. So what's the greatest common factor? 35. Everybody follow that? Good. And since I have these two boxes, if I wanted to do, just for fun, the least common multiple, it's too far over, you can't see it. If I wanted to do the least common multiple, it would have to have this number in it, which would be 3 and 3 and 5 and 7. Agreed? And it would have to have this number in it, which is 5 and 7 and 2 and another 5. You follow that? I already had the 5 and the 7 in there, so I just have to add the 2 and the other 5. So now the least common multiple is what? 5 times 5 is 25. Well, let's just go. 3 times 3 is 9, times 5 is 45. 45 times 7, you got your calculator handy? What's 45 times 7? 215? 45 times 7. $315, and then times 2. Wait, 2 times 5 is 10, so take that times 10. So the least common multiple is 3,150. That would be making a lot of multiples, wouldn't it, to find that one? So that's where you can use these factors to find least common multiples. Okay, let's go back over here to problem 42. 12, 18, and 30. Okay, let's do, for 12, what would that be? 2 times 6, and then bring the 2 down, and what would happen to the 6? 2 times 3. 18, tell me where to start.
2 times 9.
See, whoever speaks first, that's the way you do it. Then 2, and what do we do with the 9?
3 times
3 times 3. So we have 2 times 3 times 3. And 30?
2 times 15.
2 times 15. And come down, you get 2, and 3, and 5. So here's this one, here's this one, and here's this one. Now, common factors. Greatest common. What's common? Is there a 2 in every one?
Yeah.
So I put a 2 down here. Is there another 2 in all of them?
No.
No. Is there a 3 in every one?
Yes.
So I put a 3 down here. Is there a 5 in all of them?
No.
So you see what I've done? I've looked for what's common to all 3 of them. 2 and 3. Maybe change colors here. 2 and 3. 2 and 3. 2 and 3. So the greatest common factor is 6. And we won't do the least common multiple because you don't have to do that. So we'll just move on. 46 says reduce each fraction to lowest terms. All right, here we go. Let's build a tree for 80. Tell me where to start. It's your choice. You give the numbers, it'll work anyway.
2 times 40.
2 times 40. Then we keep the 2, and what do we do with 40?
2 times 20.
2 times 20. Keep the 2, keep the 2. 20 becomes
4 times 5.
4 times 5. Keep the 2, keep the 2. 2 and 2, and 5. Everybody follow that? That's our prime factorization of 80. Now let's do 92. What would that be?
2 times 46.
2 times 46. Then we have 2, and what else?
23.
2 times what?
23.
23. Is that right? Is 23 a prime number?
Yes.
Ah, look at the chart. So this one is 2 times 2 times 23 over, or 2 times 2 times 2 times 2 times 5 over 2 times 2 times 23. What would cancel out?
2.
This 2 and this 2? This 2 and this 2? So the answer would be what? What's 2 times 2 times 5?
20.
20 over 23. Were some of you taught to reduce fractions like that earlier in life? It helps too, doesn't it? I mean, building these factor trees really helps simplify fractions. 40, what are we doing now? 50, number 50. 315, so I just did it for you. 5 times 63, 5 times 7 times 9, 5 times 7 times 3 times 3. And it doesn't hurt to circle those so you know you're multiplying all this stuff. Then 420, 5 times 84, 5 times 4 times 21, 5 times 2 times 2 times 3 times 7. So my new fraction line, what cancels?
5.
The 5s.
7.
the 7. Anything else? And one of the 3's. Wow, how cool is that? The answer is 3 over what? 4. Now that's what I call reducing fractions. Quick and easy. That right there is a good enough reason to learn this technique, isn't it? Well, I thought so. 53. One 15th plus 1/55. So I take 15 and make it 3 times 5. And 55 and make it 5 times 11. So now my least common multiple, I have to have a 3 in it, a 5 in it, and an 11 in it. So I put my least common multiple over here, 3 and 5 and 11. 3 and 5 and 11. And what do I have to take times 15? 15 is 3 and 5, right? 3 times 5. So I need to take this times 11. You follow that? To make this look like 3, 5, and 11. So I take the top times 11. So now I have 11 over that plus, this is 5 times 11. So I need times 3. So times 3 times 3. So I have 3. So I have 11 plus 3, which adds up to what? 14 over 3 times 5 times 11. And what does that come out to be? What's 55 times 3? 165. So the answer is 14 over 165. And can I reduce that down? Well, just to check it, 14 would be 2 times 7. Can I divide 165 by 2? Evenly? No. Can I divide 165 by 7 evenly? No. So that's in simplest form. Any questions about what I just did? You see how I find the least common multiple? And then use that for my denominator and then rename the fractions? And add them and get 14 over that number. Well, should we do another one of these? Number 60. $12 and $15 and $20. So I've already done the trees. Now, it has to have all 3 of these in them, so I put 3 and 2 and 2. Now, it has to have these in them, so do I already have a 3? So I just need to add a 5. And now it has to have a 2 in it. It does. Another 2, it does, and a 5, and it does. So I don't have to add any more numbers. You follow me? I've already got 2, 2, 5 in here. So I have 3, 2, 2, I have 3, 5, and I have 2, 2, 5. You follow that? So that makes this number the least common multiple. So I put that number down twice. No, 3 times. And what do I take times 12? To get this number? 12, remember, was 3.2.2. So I need to put 5 up here. So I end up with 5. And 15 is 3.5. So I need to put 2 times 2, which is 4. And that gives me a 4. And then 20 is 2.2.5. So 2.2.5, I need a 3 with it. So I have 3 on top. So 5 plus 4 is 9, plus 3 is 12. Over, what's 3 times 2 times 2 times 5? 4 times 5 is 20 times 3, 12 over 60. Oh, wait, I can reduce that down, can't I? 12 is 2 times 2 times 3. 60 is 6 times 10. 2 times 3 times 2 times 5. Change colors here. The 2 cancels. The other 2 cancels. The 3 cancels. And the answer is 1 over 5. Everybody follow that? Good. What are we going to do now? Number 64. In recent years, 1035 billion was spent on health care in the United States. Of this amount, 1/10 was drugs. See what I'm doing? I'm pulling out of here the information. I'm pulling out of here the information I need to do the math. 1/10 for drugs. What else does it say? Oh, drugs, not just drugs. Drugs, eyeglasses, and what else? And necessities. 1/4 for what? Professional services. And 2/25 for nursing homes. Is that it? And 3/20 for miscellaneous. The rest is hospital cost. What fraction of the money was used for hospital cost? Hospital cost is what fraction? Isn't that what they want to know? Well, what do I have? I have 1/10 and 1/4 and 2/25 and 3/20. What's the common denominator for all of those? I mean, what's a convenient one? 100? So this would be 10 over 100, right? This would be 25 over 100. This would be 8 over 100. This would be, what would that be? 15 over 100. Everybody see where I'm getting those numbers? So what's 10 plus 25 plus 8 plus 15? 35, 50. Did I get them all? $35, 45, 58, 58 over 100. So what's the answer to the question? How much was the last one? Hospital cost? How much out of 100? 58 out of 100 is all of this stuff. How much is there left? 42. Agreed? 58 and 42 make all of it. So reduce that down, and that would be what? 21 over 50. And it looks like that's as far as it goes, doesn't it? Because I can't divide 50 by 3 or 7. So 21/50 was how much was spent for hospital care. Let's do another one. Better put a number on that one. That was 64. Let's do another one. 66. A bookstore owner spent 3/5 of her investment on bookcases, 3/5 for bookcases, 1/10. Wait a minute. 1/10 on office machines. And the rest on what? Books. what proportion of her initial investment was spent on books? What's the fraction for books? That's what she wants to know. You follow what I do? I put down what they give me, then I look for the question. It's like, well, if the rest is books, then how much is this? 6/10 and 1/10 add up to what? 7/10. So what's the rest? 3/10. So what do they want to know? What proportion of her initial investment was spent on books? 3/10 of her initial investment was spent on books. Number 68. Do you know what is in your trash? Well, according to this, 1/5 is yard waste. 1/10 is food waste. 1/4 is metal, glass, and something else, plastic. And what's the next one? 1/8 is wood, rubber, miscellaneous. The rest is paper and cardboard. The rest is paper and cardboard. See how I'm taking what they give me and just simplifying it to mathematical terms? Now, what do they want to know? What fraction of the garbage is paper and cardboard? Well, then that just means, what do I do with, change colors here, with 5 and 10 and 4 and 8? What's the common denominator? 40. So we have and 1/5 would be how many 40ths? Times 8, times 8, 8. 1/10 would be how many 40ths? Times 4, times 4, 4. 1/4 would be how many 40ths? Times 10, times 10, 10. 1/8 would be how many 40ths? Times 5, times 5, 5. So 5 and 10 and 4 and 8 add up to what? 12, 22. Is that right? 27 over 40? So what would be the fraction down here? If the total is 40 over 40, and this is all 27 over 40, what would be here? 13 over 40? And I just found the answer to the question. Does everyone see a technique for solving story problems that I'm doing here? You take all those words and you boil them down to a few bits of mathematical information. Then you write down the question they're wanting you to find, and then look at what do I need to do to find that. And stop when you get to 69. You've gone far enough when you get to 69. Because we're out of time. And I will turn this off for a minute. Thought I would. Oh, here we go. And get ready to help you with your